In most of my lessons, I start with the theoretical and then I work into the practical. For this lesson where we start learning how to evaluate limits analytically, I'm going to do it the other way around. I'm going to sort of show you a practical approach for how to evaluate limits, and then after that we'll talk about sort of what this is all meant. So when you want to evaluate a limit analytically, I really feel like the first step is attempt to plug in the number. Sometimes it'll work. When you attempt to plug in the number, there are sort of three things that are going to happen, so we'll go over those things now. So the first thing that could happen when you attempt to evaluate the expression for the given value of x is that you could get a number. If and or when this happens, generally speaking, that number is the limit. Unless you're dealing with a piecewise function or some other very strange thing, if you've got sort of a nice normal looking function and when you attempt to plug in that x value, it evaluates to a number, that number will be your limit. I'll be honest, this is sort of the easy case, this is the nicest thing that can happen, and because of that it doesn't happen terribly often, but it can, and keep in mind your first step should always be attempt to evaluate the expression for the given value of x. Attempt to just plug in that x value. If it works, if you get a number, you're done. Okay? The next thing that can happen, and I'm going to sort of write this over to the right, the next thing that can happen is that it evaluates to a number over 0. And more specifically, what I mean to say there is that when you attempt to plug in that value, if you get some number that's not 0 divided by 0, so if you end up with, like 5 over 0, or negative 1 over 0, or, 503 over 0, if you end up with anything like that, it immediately means that the limit does not exist. More specifically, the limit doesn't exist because the function has a vertical asymptote there. In math analysis, and even back in intermediate algebra, you learned that if you ever have a place where a function has division by 0, like 5 over 0, that function is going to have a vertical asymptote there. Okay. The third thing that can happen, and sort of understand these two things are sort of the easy cases because you don't have to do any more work, you're sort of done. The third case, and the one that requires more work, is if this limit evaluates to 0 over 0. When the function evaluates to 0, I sort of have a silly expression that I say, when you get 0 over 0, it effectively means you have to try harder. Every limit will end up falling into this category or this category in the end. So if you've got a limit that evaluates to 0 over 0, it means you need to do something. And the tactic that we're going to use today is factoring. Right? So when you get 0 over 0, the limit might exist, it might be this one, or the limit might not exist, it could be this one. We're going to need to work with this expression more. So just to reiterate, when we evaluate limits analytically, we attempt to plug in the x value, and one of three things will happen. Either you'll get a number, which means you're done, the limit existed. The other thing that might happen is you might get some non-zero number divided by 0. When that happens, it means the limit doesn't exist because the function has a vertical asymptote. The third thing that can happen, and the most likely thing to happen because the problems are the most interesting, is that the expression evaluates to 0 over 0. When that happens, we have to try harder, and for today, that's going to mean factoring and sort of canceling or simplifying the expression, and trying to evaluate again and finding it in either one of these two categories. So I've now got several examples we'll take a look at. So this first example, I'll evaluate this limit analytically. So try and follow the flow chart of work that we had on the previous page for this problem. So step 1, in fact the only step that I numbered on the last page, was to attempt to plug in the number and see if it works. Right? So when I try to evaluate this expression right here for 5, I end up with 3 times 5 minus 1. I get 14, and congratulations, that's the limit. Right? This expression wasn't wacky. It's not like it was a piecewise function or some crazy thing we've never seen. It was a fairly nice, normal-looking function. I plugged in my number, it worked. This is the limit. As this function, as the x values get close to 5, this function's value approaches 14. Okay? So next example. So evaluate this limit analytically. In this case, you may have forgotten how to evaluate the sum and difference of cubes, so I'll sort of walk you through that really quickly. I'll do a separate example and let you do that one. So suppose that you were asked to factor x cubed minus 8. So the way that, and actually I'm going to do this, let's say you had x cubed plus or minus 8. The way that I've always seen these is that it factors into a binomial and a trinomial. Right? The binomial uses sort of the same terms you used before, so it's going to use x and then plus or minus 2. So, this was x cubed, this is effectively 2 cubed. If this was x cubed plus 8, this would be x plus 2. If this was x cubed minus 8, it would be x minus 2. Fair enough. Then for your trinomial, there are going to be 3 parts, right? The first part is the first expression squared. So we're going to start with x squared. The last expression, the last term here, is going to be the last term squared. So you're going to end up with 4 here. And the middle term is going to be one of each of them. So this one was x times x, this one was 2 times 2, and the one in the middle will be 2 times x. So we'll end up with 2x here. Now all we need are the signs that go in between. The final sign is always a plus, and the first sign is always the opposite of the one that you used here, so the opposite of that one. So it'll sort of be minus or plus. Okay, so that should give you an idea for how to factor sum and difference of cubes. I now want you to use that for this problem. So our first step is to attempt to plug in 3. When I attempt to plug in 3, I end up with 0 divided by 0, and so that means I have to try harder. Right? So try harder means do the limit again. So actually write it out again. We'll write the limit as x approaches 3. And now, factor this thing, simplify this thing. So I'd like you to pause the video and try that on your own. You should end up with x minus 3 on the top. On the bottom, you have x minus 3 times x squared plus 3x plus 9. And at this point, we recognize that the numerator and the denominator both have an x minus 3, so those can be removed. And the problem is now the limit as x approaches 3 of 1 over x squared plus 3x plus 9. Now, and this is the important part, this is now basically a new limit, right? And how do we approach all limit problems? We attempt to evaluate the expression for the value of x. So what happens when I attempt to plug in that 3? Well, now I end up with 1 over 9 plus 9 plus 9. In other words, I end up with 1 over 27. So notice that I started with 0 over 0, which meant try harder. I simplified the expression, that gave me a new limit, and when I got that new limit, I tried evaluating again, and this time it worked. That means this limit does exist, this limit is 1/27. So now this example, evaluate this limit analytically. So pause the video, try this one on your own. You should be able to follow the principles pretty simply. So for this one, I want to take this limit, the first step we take in doing a limit is we attempt to plug in the number. So when I try to plug in -2, I end up with -6 plus 6 over 4 minus 8 plus 4, which ends up getting me 0 over 0. Sorry, that's supposed to be an arrow. Ends up getting me 0 over 0. We know what 0 over 0 means try harder. So to try harder, we rewrite our limit, and I simplify. I factor, right? 3 times x plus 2 over x plus 2 times x plus 2. Okay? Well, notice that there's an x plus 2 that will be eliminated from the top and the bottom. When I do that, I have the limit as x approaches -2 of 3 over x plus 2. And now what happens when I attempt to plug in -2? I end up with 3 over 0. And so what does that mean? Right. This means that the original expression has a vertical asymptote at -2, which means the limit does not exist. So this was another example where we did a limit and it was approaching 0 over 0. That means we try harder, we simplify the expression, and then we attempt to evaluate again, and when we attempt to evaluate again, this time we found that the limit didn't exist. So one more example for you to try. Go ahead and work this one out. So we attempt to plug in 10. When you plug in 10, you end up with 0 over 0, which means try harder. So to do that, we factor, because that's the only trick that we know right now. The limit as x approaches 10. So this is difference of squares. 10 plus x times 10 minus x, all over x minus 10. And I hope you remember from intermediate algebra, or algebra for that matter, that when you have two things like this, two factors that are the same but one of them is backward, what we can do is we can effectively factor a negative out of one of them. So what I'm going to do here, I'll have the limit as x approaches 10. I'll have 10 plus x. Then I'm going to factor a negative out of this one. I'm going to make this negative x minus 10 over x minus 10. Now we can see that these two terms, these two factors, will eliminate one another, and the limit that we have left when this simplifies, the limit as x approaches 10 of negative 10 plus x, which means when I plug 10 into that, I'm going to end up with negative 20. So once again, we started with a 0 over 0. That meant try harder. We factored, we canceled something, and now when we evaluate in the end, we get a value. So this limit does exist. This flow of problem is how we're going to handle pretty much all of our limits. There are going to be some different techniques that come in, but this is the idea, so I really want to make sure we get a strong hold on it now.